I really have no idea what kind of audience we have. So it's not very structured, and I'll try to sort of just guide it in some way that seems to be keeping people happy. But I was very impressed by the way the material of this talk has been set up in the previous lecture. So at least for the first 30 minutes, it should be possible to follow something. Okay, so, and I'm going to go back, way back in time. So we're going to start off sort of 30 years ago when these marches aléatoires were being employed in algorithmic contexts. Okay, so as we see from the title, we're talking about sampling. So we're thinking about combinatorial structures, possibly from computer science, possibly from statistical physics, or approximately counting them. And it turns out, though I'm not going to go into this in any detail, that these two things are intimately related. So that if you can solve one problem, if you've got a class of combinatorial structures you want to sample from, then it's possible to approximately count. And I guess there's a hint of that in the previous talk. And it goes the other way, that if you can approximately count things, then typically you can use that as a black box to do with sampling. Oh dear. Okay, but I guess I can always... okay. This works. Yeah, let's go back for a minute. Okay, so I'm going to avoid defining things formally too much, so we'll do most things by example. And so there are going to be two running examples. The second of them particularly important, just to illustrate what it is that we're trying to study. Okay, and they look like very toy examples, which is good because we can try to prove things about them, but also, as well as being toy examples, they arise in statistical physics as models of something or the other. Okay, so in this first one, the instance is a graph. So in this case, it's a regular graph because it's a fragment of the lattice, because in physics you'd be interested in the graph being a fragment of a 2- or 3-dimensional lattice. But actually, from the computer science point of view, we're just interested in arbitrary graphs. And we're interested in the matchings in that graph. So that's the thing picked out. A typical example is picked out in red. Okay, so there are a bunch of edges which have the property that they don't collide. So if you look at those red edges, then no pair of them share a common vertex. Okay, so that's what a matching is. So there's obviously going to be an awful lot of those things if the graph is of any reasonable size. And we're interested in sampling them according to a distribution. So if we set lambda equals 1 to start off with, then what we want is just a uniformly selected random matching. A randomly selected one of those red things there. But actually, it's more interesting to, and this is the situation in physics, is to give weights to these objects. So for each red edge, we count, so lambda is a real number, or maybe a complex number later. So for every red edge, we count lambda. So the total weight of that configuration there is 1, 2, 3, 4, lambda to the power 4. And we're interested in the probability distribution, which makes the probability of being at a matching proportional to lambda to the cardinality. And this quantity on the bottom is what you need to make it into a probability distribution. So if it's a probability distribution, you want everything to sum to 1. So you need to divide through by the sum of the weights of all the matchings. So each matching gets a weight which is a probability, which is its own weight divided by the total weight of things of its kind. So that's the initial problem I want to discuss, is how do we sample from this distribution? So if you like to make it particularly simple, choose lambda equals 1. How is it that we would be able to sample uniformly at random one of those. Oh, by the way, so in physics, the story is supposed to be that this two-dimensional lattice is an arrangement of atoms in a crystal, and then these red edges, they're molecules with two atoms which stick to the surface. And so somehow this red thing is supposed to be a configuration of so-called diatomic molecules which are sitting on the surface of a two-dimensional lattice. And so they want to be able to see what a typical one looks like as lambda, and particularly as lambda varies, because the key thing in physics is there a phase transition? Does something suddenly happen as you vary lambda? Okay, so that's one problem. And then another problem which is supposed to look very similar, but of course is inevitably going to be very different when we consider it from a computational perspective. And here, it's the same game, except that it's a subset of the vertices rather than the edges. So if we look at those red guys, then it's an independent set. It means that no pair of them are adjacent. So I guess at least the laser thing will work. Right, so there's no pair. We're selecting a subset of the vertices, and we've done it in such a way that no pair of red things are adjacent. Okay, and that's called an independent set. And it's rather akin to the matchings, except that it's talking about the vertices as opposed to the edges of the graph. And the same game, we can count lambda for every vertex we select. So this is lambda to the 4. And then we can make it into a probability distribution by dividing through by the sum of the weights. So this is the total weight of all the configurations. Divide through, that means this thing is now normalized so that the total weight is 1. And we have a probability distribution. So the task, as before, is to sample from this. So if lambda is 1, the task is merely to sample uniformly at random an independent set, namely one of these things which avoid collisions. So it's the same story. This is a crystal. Things get stuck on the surface, but they don't like each other, so they're not allowed to be adjacent. And again, you'd like to know if there's a phase transition. Does something dramatic happen obviously on a much larger section of lattice than this, or a section of crystal? Does something dramatic happen as we vary lambda? In particular, do these configurations suddenly look different? So we want to know how to sample a typical configuration to see what it looks like. Oh, right. Okay, now as I said, from the title, we've got two things. We've got sampling and counting, and it turns out that they're similar. So the counting task is estimating the partition functions, so-called. So the partition function is just the sum of the weights. It's this thing that we have to divide through in order to get a probability distribution. And well, we'll see in a moment that actually, as an exact problem, this is almost never solvable. So if you want to know what this partition function is exactly, this is almost always a computationally hard task. And you can see that at least it might be a computationally hard task because we're trying to evaluate a sum, but the sum ranges over an exponential number of objects, exponential in the size of the graph. So brute force would be just to evaluate that sum, but that's going to take us exponential time in the size of the instance. So you can see that that's a that's a real computational problem. And here's the meta theorem. It's meta because you can make it into an exact statement, but only by placing sort of quite tricky technical conditions on the problem that you're looking at. But these technical conditions are satisfied most of the time, the vast majority of instances. And what it means is that if you can solve one of these problems, so for example, if you can sample uniformly at random, or you can sample according to the correct distribution, the combinatorial structures, then you can figure out how many there are, roughly, to estimate any error that you like. And conversely, if you're able to approximately count the structures, then it's possible, under these technical conditions, to use that as a black box in order to do sampling. So the nice thing is I don't have to treat these as two different problems. I just need to solve one, and that automatically gives a solution to the other. Okay, so I guess my assumption is, so the assumption I'm making is that everyone is likely to have come across P and NP to some extent. So I'll just say how these counting problems relate to what you know about. And you probably picked up, whatever your background, the idea that in theoretical computer science, the first thing that people do, I mean, eventually they want to know detailed information, but the first division is to find out whether a computational task can be done in polynomial time. That means in a number of steps which scales as a polynomial in the size of the graph. So if n is the number of vertices in the graph, then can we solve the problem in, say, n squared or n cubed time? Or do we actually need exponential time? In the case of our problems, do we actually need to explicitly evaluate those sums in order to know what the answer is? Okay, so this dichotomy is pervasive in computer science. And of course, this is a highly unrealistic view of the world, but it's a useful starting point that we regard a problem as tractable if it can be solved in polynomial number of steps, say in n squared or n cubed. And obviously intractable if it can't, and that typically means that it requires exponential, something like 2 to the n, or something like this. So the classical theory of NP completeness talks about that dichotomy. It partitions things into problems which can be done in polynomial time, and almost all the rest which are NP complete, whatever that means. But it's a class of problems which almost certainly, they're all interrelated, and they almost certainly don't have polynomial time algorithms. So the theory of NP completeness, it relates to decision problems, yes-no problems, right? But the things here, accounting problems, they're different. They're evaluation. Turns out they're even harder. So these things were, from the complexity theoretic point of view, were initially studied by Leslie Valiant back in the 70s, and who introduced the appropriate complexity class. So this is the analog of NP to counting problems. So it's a bigger class even. It's even if P equals NP, which is hardly likely, nevertheless, this bigger class might survive. It might not collapse down. And it turns out that the exact evaluation of the partition function is intractable in both the cases that we saw for both the independent sets and the matchings, and indeed for almost every other example. And the others are rather, there's one famous example, spanning trees in a graph, where Kirchhoff, even in the 19th century, knew how to evaluate the number of spanning trees by writing down an appropriate determinant. And a determinant that can be solved by Gaussian elimination, so that is a polynomial time algorithm, even if he wouldn't have thought about it in that sense. And then there's another famous example from statistical physics in the 50s, which is exactly the matching problem in 2 dimensions. And it turns out that, so for the example that I gave was certainly a 2-dimensional example. It could be written, the graph could be written down on, was planar. You could write it down in a surface without crossing edges. And it turns out there's a very cunning way, again, by reduction to determinant, which solves that. But really, these are extraordinarily isolated examples, and the vast majority of counting problems are complete for this complexity class. So we do not expect there to be efficient algorithms for them. On the other hand, so that's why there's a lot of emphasis on, oops, shouldn't have done that. There's a lot of emphasis on trying to solve these problems approximately, which means getting a sample which is close to the one, that's close in distribution to the one you want, or evaluating the partition function and getting a result which is within small relative error. So you give yourself an epsilon, and you want a solution which is within ratio 1 plus or minus epsilon. And it turns out that although those two problems looked rather similar, right? One was just vertex-independent sets, the other was edge-independent sets. Nevertheless, one of the examples is tractable and one is intractable. And because of this connection, this meta-theorem, as I called it, it has to be the same problem in both cases. So there's one of these problems that's tractable, i.e. polynomial time, for sampling, and whatever that problem is, it'll be the same problem that's tractable for the partition function. And I think a priori there's no reason to guess, there's no basis on which to guess which one is which. So that's why complexity comes in. Right, and so basically this study of counting problems from a theoretical computer science standpoint was initiated by Leslie Valiant. So now, of course, the audience knows already what solution technique we should use for solving these problems. But before we get there, let's just have a technique which fails, which is a nice idea, but we'll see why it fails and perhaps why random walks are a better idea. So let's concentrate on the matching problem. And suppose, let's for simplicity think about the weight as being 1. So it's purely combinatorial. Right? We just want each matching to appear with equal probability. So one way of doing it is dart throwing or Monte Carlo. Okay, so here, this is drawn as a square because it's supposed to be the all possible subsets of the edges. See, some of them will be matchings, and some of them will not because they'll have edges which collide. So if you choose a random subset of the edges, in general, there'll be a pair of edges, in general many of them, which collide, which share a vertex, so they won't be matchings. But nevertheless, it's a valid algorithm. So I've drawn that as a square because that's a nice set. You can easily generate from that. You just go for each edge in turn, you flip a coin, and you decide whether to put that edge in. So that's very simple. So I make that a nice simple square. Here's the set of all matchings, the sets which, in addition, satisfy this condition that every pair of edges you select do not share, they don't collide. So the idea is you just shoot darts into this ball, which we've decided is easy. We just make independent coin flips for each edge. And if it happens that we select a matching, then we return that as the result. But more generally, we select something which isn't a matching. In this case, we just throw it away, it's no good, and we throw another dart. So it's valid, it's a correct algorithm in the sense that when it eventually halts, it will halt with a uniform random matching. You can imagine, right, if you make uniform throws into that square, then if you reject the guys outside, then what's left inside will be a uniform selection from within this set. So because the set of matchings is a much more complicated combinatorial affair, I've drawn it sort of wiggly. But the most important thing is this is tiny. This good section is exponentially small compared with the totality of subsets. Right? Because I think each vertex has a chance of being one of these hits. And so, you know, the probability that you're going to miss a hit in vertex 1 and vertex 2 will miss being the meeting point of two edges. And each of these multiplies, and so there's an exponentially small probability that you'll land up here. So the trouble is, it's correct, but you'll have to make exponentially many trials before you get a success. Okay, so we need some other idea, which we know is to do a random walk. So this is a blow-up of the last slide. So you can see this is the crazy set that we have to sample from. And before, we were just naively throwing darts and missing this nice section. On the other hand, we can easily find something in here. For example, we could start with no edges at all. That's certainly a valid matching. It's certainly, if you have no edges in it, it's certainly not going to have any collisions. So there's no problem finding something in here. The problem is finding a uniform sample from here. So how do we do that? We just do a random walk in this space. And here it is. So the nice thing about random walks is that they tend to be very simple algorithms. That's one good thing. And the other good thing is it tends to be very difficult to prove anything about them. So it's that sweet spot, really. So what you do, how do you move around this space? Well, it's easy. You're at a current matching, which is a subset of edges. You choose an edge uniformly at random, and then you take the symmetric difference. So if if this edge E is in the matching, you take it out. And if it's not in the matching, you put it in. Now, of course, if you take an edge out, that's going to be a matching, so that's fine. But if you put one in, there's a chance that it will collide with something already there. Okay, so this M prime may not be a matching. If it is a matching, then we're happy. And if it's not, we stay where we are. So the idea is we try to make a move randomly. And if we move outside the blue zone, then we just, well, if we attempt to move outside, then we just don't. Now, with these, okay. So with these kinds of Markov chain, it's the easy bit is seeing that they eventually reach equilibrium. So this is classical theory of Markov chains. You can pick off any textbook, undergraduate textbook, and find all this stuff. So this goes way back. So it's usually easy to see that this process, this stochastic process, settles down in equilibrium in a state in which each of the matchings is equally likely. So this is just like searching the web or something like the web graph or something like this. So that's not in doubt. Now the question is, how long do we have to wait for equilibrium? Because we're starting out in a very particular matching. How long before we forget that information about where we started from? Okay, so this, yes, I guess I should have put this slide on earlier. Here is Markov, apparently. In this case, our Markov chain, the state space, so-called, is the set of all the possible matchings in the graph. The rule for the random walk, so random walk and Markov chain I can use interchangeably. It converges to the correct stationary distribution. And if I want to incorporate that weight lambda, it's very easy to do. I just do I do a lambda bias. I make it more favorable that I add an edge than I subtract it. Okay, so the more complicated distribution with the weights in is something I can easily achieve as well. And we're interested in the mixing time. How long does it take to converge to this state that we're interested in, which is, so that's the idea. We start anywhere, we run the Markov chain, it converges to equilibrium. If we're sufficiently close to equilibrium, we stop the chain, and where we are now is the sample that we want, close to the desired distribution. Okay, so now I think this is going to, so I think I will go through the very vague idea of how one proves that in the case of the matchings chain, convergence is rapid, and then I'll hint about as to why the convergence is not rapid in the case of the independent sets. So I don't think this is going to be completely comprehensible, but except that at some point there'll be a picture, and I think the picture will explain the symbols. But roughly speaking, the idea is between every pair of states of a Markov chain, you define a path in transition. So you choose very carefully a way that you can get from one state, which is a combinatorial structure, to another state. And you do this using the valid transition. So obviously, for the matchings, a valid path would be take all the edges out of the initial state, so I've got the empty matching, and then put them back one by one until I get to the matching that I want to end up with. Turns out, I mean, that's valid, but it turns out that for this application, that would be disastrous. So actually, I'm interested in very carefully selected canonical paths, so-called, which spread the flow throughout the state space. And in particular, what I just suggested was very bad because it routes everything through the empty matching. So I want something the opposite of that. I want something which uses the whole state space to do the routing. So this formula, I just say in, ooh, okay, okay. On the left, you can think about this as flow. So on the left-hand side, this is somehow measuring. So we fix attention on a transition, which is from Z to Z bar. So this is some state. This is an adjacent state that we could move to, and we ask how many canonical paths use that transition. And for each of them, we have a flow. So we charge whatever the probability of the initial configuration is, whatever the probability of the final configuration, and the length of the path, the number of transitions on the path. And that's our notion of flow. So for each transition, we measure the flow, which is a measure of how many paths use that transition. So that's a flow. And if you know network flow, it's like that. On the right, we have the capacity of the transition to support that flow. Okay, so it's something to do, this is the transition probability, the probability of going from Z to Z prime, given that you're at Z. And this is the probability of being at Z. So actually, this is the probability of being at Z, and then at the next step, making the transition to Z prime. And so this relationship here there's a constant, which I assume is going to light up in, oh, it's not, okay. This constant is saying, if it's small, that's good. It's saying that the flow through each transition is not much greater than the capacity of that transition to support the flow. So if rho, as it's supposed to be, is small, then I'm very happy. That means that the paths are very well distributed. Whereas for the example that I gave, where I just took all the edges out and put them back in again, then if I looked at the transitions which involve the empty matching, well, everything would route through there. So my left-hand side will be immense because it would have every canonical path. But my right-hand side will be quite small, so I'd need a massive row to compensate, and that's bad. But it turns out that there is a much better choice than that, which avoids this problem, and we can make row quite small for that particular example. And then we can use this, this theorem, which originally in some form came to us from Diaconis and Struck, and in the form that we use it now is from Alistair Sinclair. And it says that the mixing time, how long we have to wait to get close to equilibrium, is basically this congestion constant. So if we can make that congestion small, then we have mixing approach to stationarity rather rapidly. And there's another factor here, which is, which is generally, let me say, without saying what it is, it's generally n in an example. It'll be the number of vertices or the number of edges. It'll be so it's non-trivial, but it's easily computed and it's totally explicable. And you can sometimes get rid of it, or at least make it smaller. So that's the objective. But you have to, as I suggested, be very careful how you choose these canonical paths. So that's where the work is. Okay, so this is supposed to be the method in a picture. So there are two directions, which are both valid, and the easier direction is that if this is supposed to be a Markov chain, so this is getting quite impressionistic. That's a Markov chain, and you're making moves in here. And here's a constriction. So these are states, these are transitions which form a cut, a rather small number of transitions which form a cut. And intuitively, this makes equilibrium hard to achieve, right? Because if you start off on the left-hand side, you'll wander around here, and it will take a long time before you escape into the right-hand side. So such a constriction is bad. It means the mixing time is long. And it also means, if you think about trying to get flow from the states on this side through the canonical paths to the states on this side, there's going to be immense congestion here. So if there's a constriction in the state space, then that parameter rho that we had on the previous slide will be large. But the more interesting direction for us is the opposite, which is harder. I mean, none of these are hard results. There are a page or two. The other way round is more interesting. It says, if the Markov chain is rapidly mixing, it converges to equilibrium, then there is no such constriction. And then there will be a choice of the canonical paths which avoids these congestions, and rho will be small. Okay, so both directions are valid, but one you can sort of easily see, and the other takes a little bit of work. Now, the next bit I am going to just leave out, which is to say how you would manufacture these canonical paths. So I think we'll skip right through this. So this was explaining how to get from a blue starting point to a red starting point in a more subtle way than just ripping out all the blue edges and putting back all the red edges. And so trying to do it in a way that avoids the hotspots. And roughly what happens is you put the red and the blue, so you're trying to get from the blue matching to the red. You superimpose them, you discover you have some paths and cycles, and then each of those paths and cycles you can correct locally. And this turns out to be a much better thing to do. So, for example, that cycle, to get from that's where it started off, in the blue matching. We take an edge out to give ourselves some space to move around. We can't move around otherwise. And then we can make moves which slide. I didn't tell you that we introduce another move into the Markov chain. It's not essential, but it makes life a little bit easier. And then we can slide the edges round and get back and get to the red matching. So that's just a hint about how you design the canonical paths in order to sort of make sure there are no congestion. Actually, sorry, I should have said at the outset that any questions do interrupt. Okay, we won't consider how it is that we prove then. These are some slides which just hint about how you might prove that this is a good selection of random paths and actually get hold of the congestion constant. However, it can be done. And this is stuff going, well, this is going back a ways now. This is going back to the 90s. So with Alistair Sinclair, we computed this congestion, and it's kind of not too bad. So it's basically the number of vertices times the number of edges. It's certainly polynomial, at least. And there's an issue that the bigger lambda, so the bigger the lambda, the more edges in the typical matching. And so the thing gets denser and denser. And the denser it gets, the harder it is to move around the state space. So you pay for that. And so if you try to make this lambda large, then the congestion will go up and the mixing. So this is just saying that as you put more things in, as you force more edges into the matching, it gets more rigid. Okay, so at least it's a polynomial. You can improve this a little bit. Okay, but it solves the problem for matching. An interesting case is perfect matching, where you want all of the vertices covered, right? So there are no holes. That corresponds to setting lambda infinity, so this is no good. So it took 10 more years to figure out how to solve that other problem. But I won't stop now for that. So let's go back. So that's one example which is good for us, because the obvious Markov chain, or random walk that we set up, indeed converged to equilibrium rapidly, and we could use that for sampling. So we could try the same thing for independent sets, and it was looked at first by Luby and Vigoda, and later on improved results got by Bubley and Dyer. And what is the game? You choose a vertex uniformly at random, and then you flip it. Okay, and then you choose a vertex and you flip it. So the red guys, remember, are in the independent set. And then you choose a guy and you try to, okay, well, depends what your rules of the game are. But the simplest Markov chain would be to say, in that case, well, you stay put, because I can't add that guy without creating an edge with, so I'm not allowed to color the two ends of a single edge red. But another rule that makes life a little bit easier is the slide move that says, yeah, if you select a vertex and there's only one guy adjacent, then you're allowed to slide it across. So you can look at that, and you can try to analyze the mixing time. And actually you find that if you control the degree of the graph, how many edges incident at a vertex, in this case 4, okay? If you control the degree, then there will be, for a certain range of lambdas, so in this case, with degree 4, it would be okay to have lambda equals 1. So if what you wanted in this graph, or imagine a much bigger one, right, to make 1,000 by 1,000 would still be okay. If you made these very simple moves, then in not much time, actually in n log n time, where n is the number of vertices, you'll be close to having a random independent set, uniform random. But the trouble is, as lambda gets bigger, in particular when it gets to about 2 point something, then things break down. And so we don't have rapid mixing in general. So that could happen if the lambda is too big or the degree is too small. So what goes wrong? So in the best spirit of the age, I harvested something off of the web. And it looks, for a moment, so this is a two-dimensional grid. It's this square grid, of which we were looking at tiny fragments of before. Just that's a 3x4 bit. But imagine a much bigger one. And it looks for the moment as though, so I got this from David Wilson, I guess, or off his web page. I guess he got it from somewhere else, maybe, I don't know. It looks as though I've tipped the grid by 45 degrees. But in fact, you have to think of the grid being as it should be, right? It's orthogonal. It's parallel to the axis, right? So it's still sitting in the same alignment as before. But what he's done is he's coloured the vertices in with these little diamonds. Okay, this may not be apparent at the back, I realise. And the reason is to bring out a certain fact that so this is at a certain critical value of the lambda. So we try to pack more and more vertices into the independent set. And what happens is the best packing is going to be, ultimately, will be a chessboard packing, right? So the best packing will be to choose all of the black squares or all the white squares. And so if you colour these with diamonds, as he's done, then... Oh, I see. The diamonds have got to go. Yeah, I'm with it now. Like that and like that. Then in these regions, which have the checkerboard pattern, they appear as sort of solid colour in the diagram. And you can see that what's happened as at this critical value, we're getting regions, in order to pack stuff in sufficiently, the configuration is having to go into a checkerboard pattern locally, but it doesn't ever really settle down into a perfect checkerboard. So I think this is at the critical moment when red and blue are still vying with each other, but neither has won at this stage. And yet you can see that they're collecting their forces together. And if you push lambda up a bit more, what will happen is that either the blue or the red will win, and it will start to take over larger areas. And now, okay, this is all very vague, but you can imagine that that is exactly like the constriction in the state space that we talked about. So we'll have the red guys, the majority red guys on the left, the majority blue guys on the right. And you can see it's hardly likely once you've achieved the checkerboard pattern, it's very unlikely that you're ever going to move off of the black squares and onto the white squares or vice versa. So this is, in statistical physics, this would be called a phase transition. A certain point, a very critical value of lambda, below which the red and the blue are fighting it out, and neither is winning. And then you go epsilon above that, and one of them wins. And that's the phase transition. And you can imagine that this is, once you've got to the phase transition, that this is going to be an obstacle for the random walk method, because the random walk method there'll be a constriction. Oh, it was far too far back. Okay, and you'll never be able to go from the majority red to the majority blue states. Okay, I'll come back to that in a moment. This is very quick. I have to put this in because it's possibly the most classic application of the random walk method. You've got a convex body in high dimensional space. The only known way of sampling uniformly at random from it is to do a random walk. Or the only way of doing it in a way that uses a time which is polynomial in the dimension is by a random walk technique. So this was initiated by Diaphragm and Cannan and then improved by various people, starting with Lovaas and Szymonowic. Okay, so that, I have to put that in. And there are other things, the random walk method, you can take these or leave these, right? You either know what they mean or you don't. Knapsack problems, random solutions of knapsacks, perfect matchings in a bipartite graph. Perfect matchings means there's no holes. Maybe the most, ferromagnetic easing model. So probably if you know any model in statistical physics, it'll be that one. And the claim is that if it's ferromagnetic, then you can randomly sample configurations using a random walk. Okay, so it's been quite successful, the random walk method. But that's going back a fair way. And okay, recently there's been some more activity in random walks for certain problems. But nevertheless, I think the Renaissance, now I'm going to have to go away from the subject of the previous lecture, but this will be, I'll have to say this will be very brief. I just want to say there's a Renaissance, and now we've got other techniques. So random walks were basically the only game in town until about 10 years ago. It's not quite true, but it's 90% true. And then it started with Weitz, who came up with a deterministic algorithm. So all the previous approaches had been randomized, right? Even the ones that weren't to do with random walks. And he used something called decay of correlations, whatever that means. And by exploring around the vertices, he got a solution to the independent set problem, which incredibly works right up until this phase transition. So this is a real surprise, I think. See, the Markov chain method actually does, but no one was able to prove that. But what he did with his new method, this decay of correlations, he was able to show that you could go right up to the phase transition and you could still get an efficient algorithm. I mean, now we can do it with Markov chains, but I'm not sure we'd have seen how to do it if it hadn't been for this approach. So that's a different technique, and it's good. The subject's beginning to mature when there are different ways of going about it. And then so I wanted to at least get this far because I think this is the most remarkable thing that's been going on in the last decade, is that it goes the other way. So once you start to get the packing, these regular packings, then the random walk method is not going to work because you can't get from one side to the other. But it's worse than that. You can show, so that is saying some particular approach does not work. But actually, what we can show now is that no approach, under the assumption P not equal to NP, that no approach will work. And so somehow this phase transition here coincides, so in the physics sense, it is completely in the physics sense. It's talking about an infinite tree, the existence of multiple Gibbs measures, whatever they are, in this infinite tree, which is what the physicists are interested in, is completely, the transition there is at a lambda, which is exactly the same as the lambda, which is the transition in the theoretical computer science sense between the tractable and intractable. And I find this amazing, but it's true. And here's the other half of it. It was started off by, so this is a sequence of improvements. I'm coming from the other direction, saying that once you have a phase transition, it not only rules out random walks solutions, it rules out all efficient polynomial time solutions, provided you believe P not equal to NP. Okay. And I think I'm going to have to go straight to Okay, there's another, I mean, once one bus comes along, you get several, so another completely different idea. But again related to physics, was introduced by Barvinok and perfected, or to the, perfected in, i.e. taken to the state it's in now, by Patel and Rechts. And this goes by Taylor expansion. So they take a point at which it's easy to evaluate the partition function, and then they do a Taylor expansion, and they see how far they can get out. Of course, they have to compute what the low terms of the Taylor expansion is, and they give a way of doing that. And then the question is, how far can you take it? Okay, so that's just another idea. And it relates to physics because the limit of their method is it's to do, you look at the partition function and for this to work, you must have no zeros locally. And this is exactly how the physicists look at phase transition. It's the presence of zeros in the partition function, poles or zeros. So again, somehow the limit of this method is somehow also related to statistical physics. So, of course, I was going at the end to talk about recent work of my own with Heng Guo, but it will, unfortunately for him, it's going to get eliminated. But it's another idea which seems to be applicable, is applicable some of the time, and I think it has some merit. And it's going back to the rejection sampling. So we saw at the beginning of the dart, you throw darts into the board. Sometimes they land in this little region that you're interested in, otherwise you reject. And what the idea that we've been pursuing is just, sometimes we have an approach which, that's an independent set. Well, it's not an independent set because there are collisions. So there are the bad guys. And the idea is you want to randomize only the bad guys because the rest of it you're happy with. Okay, everything is good outside of, there are no collisions outside. And so you would like to throw those away and randomize just on those, on the red bits. But that doesn't work, gives you the wrong distribution. However, if you go out one, so if you take the bad guys and the things which are adjacent to bad guys, and you randomize those, and you keep going. While there are bad guys, you go out, you expand out, you re-randomize. Now you're happy because that's an independent set. And, okay, amazingly, I shouldn't really say that, but the first time you see it, it looks amazing to me. When the algorithm stops, it is absolutely uniform independent set. So that is absolutely the real deal. So there's some scope in rejection sampling. It's just that you have to be very careful exactly which bits of the configuration you keep and which bits you reject. And if you do exactly the right thing, turns out this is another way into sampling. Okay, okay. So what are these? Of course, I dug this one out from a little while back, but I don't think much has happened, so probably all right. Perfect matchings. What happens if there are no holes? And we know the answer if the graph is bipartite, whatever that means, but in general we don't know. Do we know for the bipartite, this is a completely artificial and we can do it in polynomial time, so the theoretical computer scientists are happy, but the polynomial degree is very large, so we shouldn't really be happy. We should be looking for an algorithm which you could actually use in practice. Contingency tables, that's something that the statisticians would like. So these are matrices where you know the row and column sums and you want to sample one at random. Colorings, yeah, and this is a little bit exotic, so probably only a couple of people in the audience know what I'm talking about there. But anyway, it's a nice problem. And ... This is just a sample of what's out there. Okay, so I think generally it's an exciting time because we're a lot of unlike NP completeness where we know the answer all over the place right there. Here, there's still a lot of unknown problems, and whereas 10 years ago, we basically only had random walks to help us, now we've got an increasing number of tools that we can use for algorithm design. And so I think it's really, it was starting to go off the boil around 2000, 2005, but I think it's an area which is becoming quite lively again now. So, but I will stop at this point. I've already overrun.